And then I added that good where cluster you want to like that.
I think we even found that.
And then calling that and adding two because you're adding 35 students. There's a
Yeah.
I can probably take out just the last. That's great. Like 3 through 5 out of the returns for the.
Like Bertie Scott is a, in a blindfold meeting, that's higher than say, me, 16. In a blindfold.
Okay, guys, good afternoon. Today we will work on the notebook for quantization. And I want to say that I figured out the problem with several students had an issue with stopping generation in the homework 6 on ChatGPT. So the problem is with the versions of the libraries. So I used the last versions of the libraries, and they don't have this functionality. So if you want, yeah, to make it work in that homework on what is called chain of thoughts, you should use these packages instead of updated version. Yeah, sorry, I didn't check that, and this was the issue. So today we will talk about two approaches to quantization. One is NTR, RTN, rounding to the nearest, and the other GPTQ. Okay. And we will use this previous version of the transformer library. So, well, the other announcement, I decided to skip last 2 weeks of classes, and I hope you learned what is that large language models, and to leave this just for project. So we will have two more weeks on retrieval and domain adaptation, and then you can work on the project. I hope you don't mind to, for this plan, because main goal was to learn to teach you transformer models and how to use them, and I think now you have pretty good understanding of this. So yeah, next week I will create a spreadsheet for groups, for projects. And yeah, in this homework, we will start it today on quantization. There is the part to implement this GPTQ algorithm, but I also let's see. Yeah, I also left this for if you want to implement for as a project, because I don't know how the students in this Yandex school could do all these homeworks, because it's huge. Because it's huge to implement this brain compression algorithm, and of course, you just need to fill in some gaps, but still, and then Torch doesn't have int 4, it has only int 8, so they asked to use one byte to store 2 weights of the model to get this kind of in 4-bit. Okay, if you want, you can do this, and then also bonus the modification of this algorithm. So you can do this as a project, but not as a homework. So we will just implement round to nearest, the simplest algorithm. Okay. I just wanted to show also on their GitHub, they have another homework for the same book, speculative decoding, that also can be the part of a good project. When you remember, we use a smaller model and then larger model. And there was another notebook. I can find it now, but also they measured the total weights, sum of weights for model and quantized models and plotted the plots. So, for example, for this llama 2, if we upload the weights, actually I should run the code to upload maybe a llama for now. Then it will take about 8 gigabytes, so you can't fine-tune this model because the gradients will also increase twice the capacity. And the quantized model was about 1/3 of the original model. Okay, so the first step is to convert a number and a float number into 4 bits representation, but not between -7 and 8, between 0 and 15, into unsigned int. Okay, let's do that. And here is the first function that we will implement. Given the input tensor x, apply transformation to x to represent it with an integer between 0 and 15. And here they ask to use the formula x over scale plus 0, and we want to return this scale parameter and the shifting parameter z. Okay, let's try to figure out. So we have x. Do you remember how to shift a number into range 0, 1? Oh, actually, we have an array of x's, x1, x2, x3, xi. So do you remember how to shift all the values into range 0, 1? Min-max scalar is from machine learning. So we subtract minimum, and divide by the range, max minus minimum. In this case, the smallest value of x will be 0, min minus min. The greatest value will be 1 if we divide by max minus min. So this is how we shift the data into range 0, 1. What if we want to shift into range 0, 15? We should multiply by, let's see, by this number, max absolute value. So times max abs. And now we want to get this formula, x over some number scale plus this shift parameter 0. So what will be the scale? The scale will be max minus min over max abs. And the shift parameter will be mean over this scale. Okay, so we're now ready to code this. So scale will be how to calculate the maximum value of the tensor along the rows. Torch max, I believe. Torch max of x along dimension 1. And so this is max. Okay, let's use like max value. And then we should calculate minimum. Minimum. Then the scale will be oh, you're using GPU. Yeah. For now, I don't need GPU. Let's change runtime. Oh. Okay, maybe it's okay. If I lose GPU hours on Collab, I can do one. Okay. Because I don't want to install the dependencies again to run the first cell. So scale will be max minus min, max value minus min over max ups, and the 0 will be the shift will be negative min over scale. Negative min value over scale. The only thing is that max in torch returns end value and index. So we should use dot or slice the first like of 0 or just let's see. right? Says unsqueeze. Let's see if we use just slice 0, because otherwise it returns a tuple. And the other thing that we divide by the difference, and this difference in very rare cases when we have just 1 point can be 0. So if the denominator is 0, then then let's see. Then it means that x actually coincides with mean, so it will be also 0. And it doesn't matter which scale to use. So let's use the if scale. Okay, it suggests correct code. If scale is 0, then the elements with these indices, we can assign an arbitrary number, for example, 1. But again, it's very unlikely that we will get 0 when we subtract some floats. Okay, let's look at the assertions. Scale is wrong shape. Okay. Actually, it gave me a good suggestion, use values and squeeze, but we can do unsqueeze here. And along, I don't know which dimension. Let's use the last just dimension. Okay, and all tests passed. Okay, so this is the scale. Now we want to round up the floats up to nearest integers, because it's called round to the nearest method. So let me remove my drawings. So quantize. We have a input x, we have scale 0, and we have the number of bits. So and the result we will cast in torch unsigned int 8, because it doesn't have int 4. So let's see. If we have the number of bits, then we can calculate the max epps, the range of our points. So let's calculate max epps. It will be 2 power number of bits. Minus 1. Like 15 is 16 minus 1. And then, it suggests, I believe, correct code. Let's see. Torch round. X. So yeah, it's correct code. Let's see. So we round, so we calculate, first we shift the range into 0 up to max absolute value. Then we apply rounding. And then to avoid the rounding up to like 16, we also apply the clamp. Okay, it looks correct. But just the name should be quantized x instead of x quantized. Okay. The second function, dequantize. Dequantize will okay. We'll take the input in int8 type, and then we should convert to float 16 or whatever data type of our scale and 0 was, and how can we convert back? We should multiply this number by scale and subtract 0, I believe. Check my code. Yes, we should subtract so how to get the number x from this expression? So for example, y equals x over scale plus 0, it will be y minus 0 times scale. It's our dequantize. So it will be minus and times scale. So why I didn't write quantize x minus 0 and everything multiply by scale? Because quantized x has int type. And if I would subtract 0, 0 has the float type. But if I multiply first by the float, it will be float, and then so it just easier than cast our int into float and then perform operations. Measure and quantize. So here we will estimate scale and 0 and quantize and perform quantization in this function. So the first step is, let's see, maybe it provides correct suggestion. Yeah, it looks correct. So yeah, let's see if this code actually will pass our assertions. It looks correct. Yeah. So in my code, I created this additional variable max apps, but in this suggestion, it uses the explicit value 2 bits minus 1. For max apps, apply our function get scale and 0, and then applies the function quantize to get the quantized x. And when we have quantized x, scale, and 0, we can get back, we can reconstruct, of course, with error, but we can reconstruct our original X to dequantize if we know the scale and zero parameters. Okay. What's next? Next, we want to apply this quantization to linear layers. And this code is written for us, so just run it. Okay, now we will read the weights of language model, and we will read this on our drive. So create the folder and upload the model in this folder. We will quantize, so it's an interesting that CPU doesn't support float 16. So if we want to quantize, we should quantize on GPU. The model doesn't fit on GPU. So what we will do, we will take one layer on GPU, quantize, and then put it back, then take the next layer, and well, if you don't have enough space memory, then you should do this incrementally. Um, okay, it's uploading. Okay. And this code is written for us. I mean, this process. So first we upload model on GPU, but without linear layers. So we skip initialization and we skip the uploading the weights on GPU. So we will store only li linear norm layers and the heads in the float 16 precision. That's it. But we won't upload other weights. So then we will search for layer names and indices in our dictionary of the layers. And then in this replace submodule, we will replace the placeholders with quantized layers. So, okay, here's our code. For all, so in this model, there are 32 transformer layers. So for I in range 32, we should, let's see if this goes correct. Get quantized weight scale and 0 and replace submodule. Okay, it looks correct. Yes, it looks correct. So we apply the function that we wrote earlier to get the quantized weights scale and 0 for every weight. For every weight, we will have its own scale and zero, and they have the same shape as the weight matrix. Then we will apply this function, quantized linear, which will actually quantize the layer. Again, it quantizes only the weights, it doesn't have biases. Let's see. It does have biases, but maybe this function expects bias, so that's why there is also linear bias. And then replace submodule. Let's see if we pass the tests. Okay, we passed the test. And finally, we will apply this to the entire model. So we initialize our folder, the precision. Again, it will use 8 bits, but yeah, there's additional task to use 1 byte for 2 ways, but we will think that we use 4 bits, and at least we will use 2 power 4 is 8, so well, 2 is 16, so we will use 16 integers to represent our number. So let's see. If, okay. And now this is the process when we read one layer, upload on GPU and so on, and quantize and return it back. And we will get quantized model in 4-bit precision. Yes, if another reason why I didn't want to include GPTQ, because if you want to apply this algorithm for quantization to run on this model, it will take half an hour just to quantize, because you remember it goes like feature by feature adjusting these matrices. So maybe it's okay for project, but not for yeah. This will it should be done in about 1.5 minutes. And then there is the function that tests the performance of your model. So it will be your homework to run this quantized model with the simplest approach to run on test and check the performance, compare performance with not quantized. So here's some tests like questions, and let's see how the quantized model will answer these questions. Yeah, and here's David. When I saw this early stop and true, then I realized that in homework for GPT we had, because originally I ran this code with updated packages, and the answers, so it worked for all the functions, but the answers were just a garbage. And then I remembered that they updated the Llama dictionary, and then I ran with old parameters, and then actually the answers were, we'll see it now, the answers, at least for me, were reasonable. And then I realized that to make work on that homework, we should use also like old transformer library. Well, and it makes sense because this course was created 2 years ago, and in 2 years, maybe 10 more versions of this transformer library were. Okay, let's print the answers, and you can see that the answers are pretty good, even though the model is now compressed with very simple algorithm for quantization. Can you explain the Pythagorean theorem? Says that the sum of square. Yeah, it's even correct. Not only looks like reasonable, but it's correct. What about, yeah, Shakespeare? Yeah, it's also correct. So for homework, I will ask you to just implement this evaluation because it will take a little bit more time to run it on a batch of samples and just run this test model. So you don't need to write any code. Yes. And then it calculates its perplexity. PPL stands for perplexity. As you remember, the lower perplexity means the lower cross-entropy loss. Okay. Actually, that's it for today. And yeah, because we won't go to implementation of this GPT-Q. I have this implemented, but I don't want to do this now. And yeah, so let's think about your projects. I think, yeah, I will put next week this spreadsheet. For now, I should grade your previous two homeworks. I had to grade midterm for machine learning class the last weekend, so a lot of grading, but I will grade by next class. Okay, do you have any questions, guys, about anything? Yes.
How do you feel about speculative projects for the final project in this course? I have a project idea that I'd like to try, but I'm not sure that it will work.
Yeah, so I mean, do you mean the code that they have as a homework?
No, I wanted to try fine tuning against the new ARC AGI2 benchmark and seeing if I could build a model to work on that.
No, I mean, any project is absolutely fine. So I mean, Robert, it's I think it's important to do what you're interested in. If you're interested in reinforcement learning, then maybe you should choose reinforcement. And if you're interested in this speculative generation, we don't have any limits.
It's okay if it's a bit exploratory. We're not sure if
Yes.
lead to improvements.
Yes, absolutely. It shouldn't be like the new top conference paper. Okay, let's stop.